This video is an introduction to permutations and factorial notation. Our goals for this video will be to first introduce you to the concept of a permutation. Then we will go through two examples involving permutations, and finally, I will introduce you to something called factorial notation. Let's begin by ensuring that we understand what the word permutation means. Its definition says that a permutation is a specific arrangement of distinguishable objects in a definite order. A specific arrangement of students in a class photo or a list of top 40 songs for the week are both examples of permutations. In both of these scenarios, we have distinguishable objects, so different students in a class or different songs that are placed in a particular definite order. If I were to look ahead at the next week for the top 40 songs, I would see a different possible permutation. When we work through counting problems, we are often asked to count the number of ways items can be selected and arranged in a particular order. When we do this, we are counting the number of possible permutations. For example, we may count the number of ways runners could place in a race, the number of possible pins or passcodes to a phone, or if we wanted to connect this to biology, we might count the number of ways the chemicals in our DNA molecules can be arranged that create different genes. The thing I want to stress here is that in all of these scenarios, order is particularly important. Before we get into a specific counting problem, let's take a look at these three circles. How many different ways could we arrange or order these three different circles? I'd like you to pause the video and take a stab at trying to figure this out. When you're ready, press play again and we'll take a look at all of the possibilities. All right, let's double check that you were able to draw each of the possibilities. You can see here that there are 6 possible arrangements, 6 different ways to order these 3 circles. Each arrangement is distinct. Therefore, we can describe that there are 6 possible permutations for these 3 distinct circles. Now let's add some context by going through an example. Our example reads, determine the number of arrangements that 6 children can form when lining up for a drink. Like usual, I'm going to start by drawing a diagram to help me visualize what's going on here. So here I've placed my water fountain and I've used 6 lines to represent the possible spots available for students to line up in front of the fountain. Let's begin by analyzing the first spot available. Since there are no students currently standing at the water fountain, I have 6 possible students to choose from. Now, when we get to the second spot, we have 5 students left to choose from since one student has already been chosen to lead the line. In the third spot, I'm sure you can guess that now we have 4 students left to pick from, and so on and so forth. I would continue on with this pattern until I would only have 1 student left to fill that last spot in the line. Now, since I'm doing 6 simultaneous tasks, or I'm choosing a student for the first spot, and choosing a student for the second spot, and choosing a student for the third spot, and so on and so forth, I know that I can use the fundamental counting principle to help me determine the number of arrangements. So I'm simply going to take 6 times 5 times 4 times 3 times 2 times 1, and that tells me that I have 720 possible arrangements, or 720 possible permutations for the children to line up in front of the water fountain. Now, you might be asking yourself, well, this diagram is nice and all, but if I had 25 students to line up, or if I had 500 objects to put in order, Isn't it going to take me a long time to draw out that diagram and multiply out all those factors? You'd be right. So lucky for us, we have a more concise way to write out expressions like this. We describe it as factorial notation. Let's take a look. Factorial notation is a more concise way to write out the product of consecutive descending natural numbers. Wow, that's kind of a mouthful. Let's look at this complex looking expression and see if we can break it down a little bit. N represents the total number of objects that I'd like to arrange in a permutation. I read this little expression as n factorial. So that exclamation mark represents factorial. Now this n factorial means that n is the first of my factors. And then to find my second factor, I would simply subtract 1 from n, since that's the next number in my list. The next factor would be 2 less than n, and I would keep going until I get down to 1. Now, it's key to understand that we can only use factorial notation for natural numbers, or I might describe those as being counting numbers. So, I would never write the expression of -1 factorial because -1 is not a natural number. It's an integer. Let's connect this general form back to our example about that water fountain. In this example, I ultimately ended up multiplying 6 times 5 times 4, and I kept going until I got all the way down to 1. Now, I should be able to recognize that this is in fact a product of consecutive decreasing natural numbers. I know that because I'm multiplying these numbers together. That gives me a product, and each time the factor was decreasing by 1. Instead of writing out all of these factors, now I can recognize that I just need to write down 6 factorial. To calculate that, I can use my calculator. Our calculators have a factorial button. So I'd like you to pause here, see if you can find your factorial button, and double check. Type in 6 factorial. Make sure that it's equal to 720. In general, when I have n number of distinguishable objects and I want to order them all, I can use this expression n factorial to determine the number of possible permutations. This gives us a more efficient way to calculate that circle example we did back at the beginning. We had 3 distinguishable circles and we wanted to order them all. Therefore, I could have simply used the expression 3 factorial to determine how many possible permutations I could get. Now, if we use our calculators to evaluate that expression 3 factorial, you'll find out that in fact there are 6 possible permutations. That matches up to the diagram we made in the beginning. Let's finish off by summarizing all the things that we've learned in this video. We started by defining the term permutation, and we really emphasized that order matters. Next, we counted the number of permutations in 2 different examples by using both diagrams and this new factorial notation. Ultimately, we came to realize that factorial notation certainly is more concise. And lastly, we established that we can use n factorial to help us to determine the number of permutations when we've got a bunch of distinguishable objects and we'd like to order them all.